Hello, everyone, and thank you for attending today's webinar, Improving EBSD Sensitivity Using the Clarity Direct Detection System. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all the questions asked. A copy of today's slide deck is available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I would like to introduce the presenter for today's webinar. Matt Nell is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. Matt joined TechStem Labs, known as TSL, upon graduation from the University of Utah in 1995 with a degree in material science and engineering. At TSL, he was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, Matt joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has held several roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that EBSD plays in materials characterization. In his spare time, Matt enjoys playing golf and pondering if changing the texture of his clubs will affect his final score. Now over to Matt.
Thanks, Jonathan, for that nice introduction, and welcome everybody. I'm very excited to present this webinar showing some of the capability, primarily improving the sensitivity of the EBSD collection using our new Clarity direct electron detection system. This is a product we've just introduced this year, and I'll go through a little bit of the history of detection technology, talk about direct electron detection, focus a little bit on sensitivity, how the detector works, and some application examples, show how EBSD pattern quality can improve using direct detection. Then I'm going to touch a little bit on some energy thresholding and some applications in that space, and then strain analysis that we can do with the Clarity as well. As I get started, as product manager, you often get to be in front of customers showing a lot of work, but this, of course, involves a lot of people. So would like to acknowledge Renee DeClos, Stuart Wright, Pat Camus, and the entire EDAX engineering team that have really put a lot of effort into both developing the technology as well as helping to develop some of these application examples. I would also like to acknowledge Josh Kasher at Georgia Tech, who has collaborated in some of the analysis I'm going to show today and discussions about the technology. So the Clarity, we launched this in May. This is the world's first commercial direct detector designed for EBSD. And it has a number of features that bring some unique benefits to this application space. It has zero read noise. That gives us high sensitivity, especially at low beam doses where we're not dealing with read noise or dark noise that's filtered out. We have zero distortion. We remove the phosphorin lens and optical pass, and we'll discuss that. It has a high dynamic range, so we can get really nice high-quality EBSD patterns through taking advantage of counting statistics. We have single electron sensitivity and detection of single electron events with the detector. This allows us to get some quantitative signal information. And it becomes an ideal detector for low beam dose applications, for high EBSD pattern quality, and for high angular resolution EBSD applications. So just to give a little bit of a background, the EBSD detection really started with what we call direct detection. So this is an example from John Venables from 1973, where the initial EBSD patterns were obtained using film. So the electrons directly interacted with the emulsions on the film as a direct detection approach. Now, this wasn't practical for automation. You have to take the film out, you have to develop it, have it, but the initial work was direct electron detection. So, we're kind of going back to this approach and bringing back some of the benefits of doing this. These initial images were very pretty, very high contrast, and that's kind of what we're going back to replicating with direct detector technology. Moving forward, in the mid-'80s, David Dingley was the first to couple EBSD with in this case, an analog camera, TV rate camera, that was coupled to a frame grabber to bring the EBSD pattern into a computer. And this was really a revolutionary step because now we could use the computer to index the diffraction pattern. And by index, what I mean is we determine the orientation and or phase from the pattern. So if you look at the pattern there on the right, you can see that the zone axes there are labeled. You can see the 001 and the 101 zone axes, which tell us the orientation, in this case, of a piece of aluminum. For this approach, the detection had a phosphor screen. So the phosphor, when the electrons hit the phosphor, this converts the electron into light photons, which then pass through a piece of leaded glass, goes through a lens, and is focused onto the analog camera sensor and brought into the computer. So the pattern quality, if you look at this compared to the early one, isn't as good, but it did allow us to start thinking about computer analysis of the patterns, and we can get automated measurements moving forward. As this technique was more commercialized going into the mid-'90s, we used what was called a silicon intensified target, or SIT camera. Again, this was an analog camera, a little bit better quality, but still noisy compared to what we can do today, and still coupled with phosphor and lenses to the camera. The next big step in technology happened around the turn of the century. This was going from an analog to digital cameras, so going to fully digital CCD cameras here, where now where the light photons are hitting the sensor and are directly digitized and can be brought over into the computer. Didn't have to be analog to digital converter at that end. And that brought an increase in pattern quality as well. And then recently, we've transitioned from CCD to CMOS cameras. This is a different type of detection circuit. This allows for higher speed readouts, again, all digital, but still relying on a phosphor screen coupled to the sensor. And so our Velocity product is built on this high-speed CMOS technology. And with direct detection, the reason we go to that is we're trying to remove some of the effects that are present due to the optical path chain in traditional detectors. So, of course, as we think about optics, cameras have lenses, and lenses have different types of distortions, and you can see some listed here. A lot of work goes into our Velocity camera to minimize these effects, and so we're still able to do EBSD, but it is still present, and they have to be designed around and minimized. And if we think of other things in the collection chain, we have our phosphor screen. This to convert the electrons to light, we have to optimize the phosphor for a given application. So we think about the different compounds that can be used to give us the right wavelength of light so that it is matched to the sensor response. We want to have light that is most efficient. We need to have a good thickness of the phosphor. We're balancing resolution versus brightness, depending on the thickness and then the grain size of the phosphor material, all to avoid basically smearing the image through kind of the cascade effect as the electrons pass through the phosphor. If we think about fiber optics, it's also possibly to couple the phosphor to the sensor using a fiber optic bundle. This brings up things like a chicken wire line effect, where you can see the latent image of the fiber optics in the image, and then as you taper your fiber optic, you'll have some efficiency losses. And with lenses, we have light losses in lenses, light losses in fiber optics, and so these are all things we've worked around in the past. But with the clarity, we can kind of go back to direct detection. And this direct detection, it's something that's been investigated for a number of years. So this is a pattern from a paper from about 5 years ago. And you can see that you get really high quality patterns because we remove the different sources of artifacts through the collection chain. We'll talk about that as we go through the presentation. And so it's a fully digital collection, still based on a CMOS sensor that's actually reading out the digital signal, but instead of having a phosphor screen, we have a detection material that converts the electron energy into a charge we can count directly without having to go to light. So just to summarize this, with direct detection, we're removing distortion, so we're counting electrons directly without a phosphor screen of the lens. Direct detection is pretty widely known in the electron microscopy community. It's really strongly developed in the TEM and the biological cryoanalysis market. And as I showed with that reference, it's been demonstrated to work for EBSD applications. But as we take this technology and work towards commercialization, there's a number of challenges that had to be addressed. The first is building and positioning the sensor and the readout circuitry into an EBSD geometry. We want to maintain the same solid angle. We want to get to be able to capture EBSD patterns that are similar to traditional EBSD patterns. That allows us to index, different crystal systems and kind of treat it transparently to things. And then as we have this detector running in a vacuum, we need to be able to manage the temperature that's generated during operation, and to be able to keep the temperature constant for good usable signals. And so the clarity has been developed to operate in the traditional EBSD geometry. So we tilt the sample somewhere around 70 degrees. We insert the detector. It's built upon what's called a hybrid pixel direct detection technology. So the detector itself has 512 by 512 pixels. It's a square sensor. It uses what we call a quad-based design. So we have 4 different 256 by 256 chips that are basically put together and mounted with a single silicon layer top sensor, which is the collection and conversion material. And this detector, it's passively cooled. It's not water cooled or anything. So all this has been designed to create the clarity. So just to highlight how this detection works, the silicon sensor layer is bump bonded to these readout chips. So there's the 4 quad readout chips. And it's designed so we can get a single electron event detection. So we filter out the baseline readout noise below a 3 kV signal level, and anything below that isn't counted. It's sort of like a discriminator on an EDS detector. We set a baseline to the collection level, and everything above that we count as an event. So if we look at our signal here, is we have a piece of silicon. There's 2 different doped regions on there with a little bit of a bias. And as the electron comes in, it creates a charge that's brought down to the amplifier. That signal is amplified. It goes into the thresholding circuit where we remove noise. If the event's above that threshold, we count it as an event, an electron event. And then we have this for the 512 by 512 array of pixels. So this is happening for each pixel. So when we do this, this allows for a high dynamic range of detection. The counter depth we have on this is 13.5 bits. So, once we've eliminated a read noise and dark current noise, the pattern quality is essentially defined by the number of electrons we count. It's just a statistical effect. And so we can count up to 13.5 bits, which is over 10,000 electrons max per pixel. This is important because, as we'll show, the intensity gradients present within EBSD, the intensity is not uniform across the pattern. So it's brighter towards the center, it's darker towards the edges. So we want a decent amount of dynamic range so we can get good quality data at the edge of the detector as well as in the center. And so when coupled with the no noise, no distortion, we really get beautiful pattern quality and sensitivity with the detector, which I'll show as we move forward. So the detector itself can be used, both for pattern collection and for mapping. So this is we call it a standard EBSD mapping. This is mapping on a dual-phase steel under what we call standard low beam current conditions. So 20 kV acceleration voltage, 2 nanoamps of beam current. In this case, running the camera at 50 points a second. So it's similar to, say, our DigiView CCD camera. The clarity itself can go up to around 85 points per second. And we achieve this. We can bin the pixels down for mapping from 512 to 512 to, say, 100 by 100 for traditional type applications where we use the HUF to detect the bands. So from this, we can see we get a regular orientation map where we color each pixel according to the crystal orientation as shown by the colored stereographic triangle here. So we can see the microstructure. And if we look at it, we can determine the phases that are present, and we can determine the misorientations that are introduced through any deformation in the sample. We can measure that through this map here on the bottom right. So we can get orientation phase, misorientations, image quality. Just like we would any standard EBSD detector, it's still possible to do that. Where this detector really has new applications, though, is being able to reduce the beam current we use below sort of normal levels. So this is taking the same sample, dropping the beam current, order of magnitude and a factor of 2, so going from 2 nanoamps to about 100 picoamps, the beam voltage 15 kV, keeping the scan speed constant, and seeing we can still get these same maps here. You can see the original map there on the top. You can see the bottom map the bottom pattern here on the right using Enpar, which I'll review in a few slides, but that's an approach where we average neighboring patterns after collection to improve signal to noise, which improves indexing performance. And I'll show some other applications of that. So we can go to lower beam currents and still get good results. And this comes from the fact that we can count the electrons and we don't have read noise. So our signal is very detectable even at low beam doses. And this is important for a couple of reasons. One, we can go to low number of electrons, which I'll show here. This is a pattern from an FCC steel sample at 10 kV, 400 picoamps essentially, and the maximum number of events or the maximum number of electrons per pixel on average is 50 electrons. And so when we think about that, and I'll show some examples, for EBSD we really have two signals. We have the diffraction signal, and then we have the scattering background signal. And so generally we do a background correction where we subtract or divide the background to flat field the image and improve the contrast of the diffraction bands so they'll be more easily detected by the HUF transform. So as we think about the number of electrons, we're thinking we want to be able to know the number of electrons but also differentiate. We want to have so we can get a signal of diffracted electrons that's higher than the background level so we can do our band detection and pattern indexing. So this is just taking this same image here, plotting it on a 3D plot, and then showing which bands are detected with the HUF. So you can see we find the positions of those bands, even with only 50 electrons per pixel. And this just will kind of show the effect. This is going to be at 2 different voltages. So this is looking at 10 kV, 400 picoamps, and just increasing the exposure time to see as we increase that the pattern quality improves because we're counting more electrons. So we're going from 50, 80, 100, so on and so forth in terms of the maximum electron dose per pixel. This does the same thing at 20 kV, similar beam currents around 400, 450 picoamps. The pattern improves as we get more electrons, but the base level at small exposure times is still sufficient for indexing. And if we make this go up a little bit higher, you can see as we go more electrons, the pattern improves in terms of signal to noise and contrast. So this slide illustrates what I mentioned just a moment ago. Is first of all, the signal is not uniform. So this is looking at, on the left, a pattern where we're looking at multiple grains. So the diffraction information is sort of averaged out. And we can see the baseline intensity distribution and then a line profile horizontally across it, where you can see that, in the center we have the highest number of electrons. At the edge, left to right, it's less. It's about a factor of 2. And if we go diagonal to diagonal, it's more of about a factor of 3 in terms of intensity difference. And so you'll see that line on the left is going through the overall background signal. That same line on the right, where we have a pattern, we've put the beam into a spot mode. Here you can see that the diffraction information is basically superimposed across the scattering signal. And so with that, you can see that there's these little bumps here. That's the information we're really trying to extract from the diffraction signal. The other thing I'll just point out on these patterns, these white crosshairs through a hair there, that's the seam of the quad detectors. So I'll show you later in the software, we actually, basically filter that out. But this is just showing the live detection so we could see the baseline pattern. So this is just a kind of a cool example. The pattern there on the left is where we have 5,000 average electrons, and that's a line profile after background collection. So you can see the amount of signal we have. It's, the range there is, say, 1,500 electrons, so plenty of electrons defining the signal. The pattern there in the middle is based when we have 10 average electrons per pixel. So quite a few less, so we'll have a little bit more in the center, a little bit less at the edge, but 10 on average. And so the range there is essentially about 10 electrons where we have a signal. But even though there's not as many electrons, visually if you look at that, you can see the diffraction pattern present, and we can still index that pattern, and we can index it with what we call high confidence, which I'll show here just in the next slide. So this is showing an EBSD map from an additively manufactured stainless steel sample where we're collecting 10 electrons on average for every pixel on the detector. And this is collected at, I think it was around 25 points a second at 13 picoamps beam current. So a lot lower beam currents than traditional applications. And we're able to, under those conditions, collect with 98% indexing success. And what we mean by that is we can get an orientation with what we call a high confidence index. So when we analyze the pattern, we assign a metric to say how unique and how strong is that solution. And it passes a threshold we define to say we believe this value to be correct. The points that don't meet that threshold are then colored black. So if you look on the image, the orientation map on the left, you'll see a lot of the black points are either concentrated near grain boundaries. That's where patterns will overlap a little bit, and it's harder to deconvolute the signal, especially when the signal level is low. And then there are 3 or 4 spots there that are pieces of dust. So that 98% indexing is also including some defects right on the surface. And we can see those spots on the Prius map there on the right, where we see some grain contrast, but we can see those black areas that correspond to points where we don't get high confidence. And that kind of shows how that confidence index thresholding works. And of course, we have our, I mentioned earlier, we have our Enpar tool. Enpar is a unique feature we have where we save all the patterns during collection. And that's where, there are more and more EBSD applications that are being developed that take advantage of saved patterns. We can do high angular resolution EBSD. We can do Enpar. We do some we call Prius analysis. There's dictionary indexing. There's principal component analysis of patterns to determine phases and things. So quite a few different applications are growing where patterns are saved. It doesn't really slow down the system to save it. It just takes up more disk space. So it's becoming more and more popular. But Enpar is one where we take a pattern and we average it with all the neighboring patterns. So our default sampling grid's a hexagonal grid, so we end up with 6 neighbors of the same distance. And when we average them together, we improve the signal to noise, but we don't slow down the system. It's essentially kind of the same benefit of frame averaging at each point. But if we frame average to get this same signal to noise level, we're averaging 7 points, it would be 7 times slower. We get the same type of an improvement, but without the time penalty. And it doesn't really have a strong negative impact on the ability to resolve features in the microstructure. So if we take Enpar, this allows us to get faster collections at lower beam current, be able to get more out of the data. But importantly for this particular result, this shows what Enpar can do for an application where we're just traditional indexing, using the Huff there on the left. The conditions that give us 11% indexing success. In this case, the low confidence points have not been colored black, but we see the speckling. If you're familiar with EBSD at all, speckling is usually bad. And then we run this same data through an Enpar processing routine, and our indexing success jumps up to 96%. We're able to reconstruct the microstructure correctly. So there's been a number of work when this was introduced to look at noise levels and things on different microstructural features. But we can take this Enpar processing and apply it to clarity, and we can go to even lower beam currents. So this is an EBSD map collected at the same speed, but going to 6 picoamps, basically going down 1 step in beam current. Our indexing under those conditions, just without Enpar, we're 82%. Certainly, that gives us a decent feel of the data. We could do some noise reduction routines to sort of enhance that. But with Enpar, we don't have to do that. We can run it through Enpar. We get the microstructure there on the right where we're at 99% indexing success. And we're directly recovering the orientation measurements. You can see within some of those regions, the blue regions, we can see the deformation structure that's present within those grains is still resolved even at these low beam doses. So now certainly for that sample, low beam doses aren't necessarily required, but there's some materials where low beam doses are required to get patterns. And one of the strongest examples we've seen recently is on these organic perovskite thin film solar materials. And so I'd like to acknowledge the group at AMOF in Amsterdam that have performed this work and shared this data, looking at different types of these materials that under traditional exposure times and beam currents, if you put the beam on a grain, the diffraction pattern basically goes away. It distorts the crystal lattice. It essentially melts the crystal. And so going to low beam doses allows us to still collect EBSD patterns and maps. So this is going to show a few different results. This is on a halide perovskite sample where we have our initial pattern. We run it through some image processing to improve the contrast and do our standard indexing. So you see here we can get the orientation very nicely of a particular pattern. And we can collect a map from a structure. The map here gives us 95% indexing success. And we see the image on the left is what we call a grain map. So the grains are randomly colored to show size, morphology. The distribution there in the middle left shows the grain size distribution. The image to the right of that, the red image, is the inverse pole figure orientation map, showing the orientation relative to the surface normal. So generally it's all red. That corresponds to the 001 orientation. We can see that on the pole figure on the top right, where there's a strong peak in the center of that pole figure. And then if we look at the radius of that, though, it's much more distributed along that. It's more of a fiber texture within the plane of the sample. So we get a very good characterization of this microstructure. Switching to another one, these are methyl ammonium lead iodide films. These were fabricated using what was called a flash infrared annealing or FIRA processing route. To get good EBSD patterns with the clarity that are persistent, we're running at lower beam doses. So this is at 15 kV acceleration voltage, 100 picoamps beam current. And you can see the map that's present. We can index this as well. And if we go to the next slide here, we can go and select one of these. I call it a starburst type of a grain, where it's a radial grain growth type of an appearance. And we can see, if we look at our image quality of that selected area, we can see that pattern image quality. And if we look at the orientation map, we can see there's a strong 112 alignment with the sample surface. And then if we come and look at these in the in-plane direction, so these are looking at the X and Y principal axes in plane. Just to kind of show how the grains are growing in plane, we can go in and draw little pictures of the crystal unit cell at different points along that radii. And you can see the different orientations that are growing along different directions. So we get good characterization of this. Then there's a third route that we're looking at, is where these are created with what's called an antisolvent approach. In this case, the grain size is much finer and the patterns are much weaker. So these are under the same conditions. You can see the as collected pattern after image stretching is still very weak. We can index that, but it's a lot weaker. So if we come and you can look at if we look at the SEM image here on the left, the grains are much smaller than the annealing approach. And if we look at the points that have orientations, there's only a few points that give patterns that are indexable. And so we can't go to longer exposure times. We can't go to higher beam currents because of the beam damage. So we save all the patterns. We run this through Enpar. This is just an example of what we get from this. So these are good patterns to start on the left. We run them through Enpar. They're significantly improved. Then we can get our indexing results quite a bit better. And so if we apply this to the sample through here, here's our area of interest. After Enpar, you'll see that the image quality starts to resolve more grains. There's some finer grains and larger grains even within these features in the structure. And then this is the original data. That's after Enpar processing. So you can see we start to fill in more of the area. So the indexing isn't perfect, but it starts to give an idea of the orientation distributions that are present and can compare to the other orientations from the other processing route. So with that, I'll take just a second just to emphasize that we can go down to very low beam doses where we're collecting very few electrons. We're average of 10 electrons per pixel. And with those electrons, we're differentiating, the diffracted signal from the scattering signal to be able to index the pattern. So that's one range of the detector. It's going down to very low beam doses. The other range of the detector is going to, fill up the entire dynamic range to get very high quality patterns. And the patterns are high quality because we're getting direct detection. We're not having to worry about phosphor blurring. We're not worrying about lens artifacts. And so this is just an example of a pattern collected with our Hikari CCD camera on the left at 527 milliseconds detection to get a high quality pattern. The clarity pattern collected in little less than 1/3 of the time with a higher dynamic range. And if you look at that, you'll see that the patterns are sharper. We have more detail out towards the edges. and there's just more information. And we can extract that a little bit more if we take these patterns and we look at band profiles along specific diffraction bands in the pattern. So this is first pulling out the 331 band and just looking at the intensity averaged along that band through there. And if you look at the Hikari compared to the Clarity, you'll just see there's a little bit more detailed information available along that profile. We're more sensitive to the transition. We're more sensitive to higher order lines. And we see that consistently if we look at different orders of bands in the pattern. Trying to just show that we get more information. And so in the end, if we look at these and put them together, the Clarity shows more detail. It has steeper band edges, more contrast between it. And the differences really are indicative of the fact that the signal changes due to the phosphor screen and the optics effects of collection, which makes sense. But it's nice to have some direct data that shows that. And so what we are able to do, we can come and look at the detail that's present in this. So this is looking at a BCC ferritic steel sample, looking at a 231 zone. We can zoom the detector by varying the position. So if we back it out, it reduces the magnification around the pattern center, which is near about the top third of the screen here, near where that 231 is. And just stepping out in 5mm steps, you'll see as we back out, the detail that's present within the zone axes. There's all these intersection lines, very sharp patterns, lots of the intersection detail as we pull it out. So we can get very high contrast information within these patterns at different positions. And so once we have that, then we can think about comparing the patterns collected with the Clarity to patterns that are simulated using dynamic diffraction theory. So this is a feature we have within a module we call OIM Matrix. This is something that's available within our OIM analysis software package, where we can use dynamic simulations to simulate more accurately EBSD patterns. So this shows an experimental pattern there on the left. We can find the orientation, plug that into the simulator, and it will simulate that pattern for direct comparison. You can see there's pretty good correlation of the features, on that zone axis there on the right, the intersection of the zone axes on the left, some of the higher order lines we can see on some of the bands. So if we compare them, we get some pretty good, strong comparisons. And in both cases, we know the number of electrons that are hitting a point either through the direct detection or through the simulation. So we can start to think about matching the intensity for different lines and different features within a diffraction pattern from simulation to experimental directly. This just shows here the detail, so we can adjust the geometry to zoom in for a simulation comparison. And again, high correlation between those. This is a similar effect for now platinum and FCC platinum around the 111 zone axis. Platinum has a lot more of the Holtz rings that are present, and just higher contrast detail within this. So, to me, it starts to very much look like some, TEM type diffraction information that's present as we back that detector out. And so now the other interesting thing we can do with our detector is, I mentioned at the beginning, we can set a discriminator or set a threshold that limits the amount of electrons, below the low energy limit. We can adjust that higher to filter out higher energy electrons. So this is, our default. Basically, we're looking at electrons greater than about 5 keV. We get a pattern like here on the left, and if we increase that threshold, we can filter. In this case, we filtered to 13, 16, and 17 keV electrons. This was a pattern collected at 20 keV. So we're cutting off electrons of lower energy to get a visualization of the remainder after that cutoff. This shows a higher resolution image of the pattern after that cutoff, you can see you start to see a little bit of a change. It's hard to see in this particular slide, so I'll show you with looking more numerically. This is looking at comparing the 5 kV band to the 17 kV band. As you'd expect, the higher the kV threshold, the band is actually a little bit more narrow. That's just because there's an inverse effect to bandwidth to voltage. And looking at the maximum bandwidth gives some idea of what electrons are contributing to the pattern we see. So in this case, we see some contribution down to around 16 kV relative to the initial 20 kV. And then below that, it really starts to become negligible. So, we can start to think about getting, more precise bandwidth measurements, maybe by filtering and knowing what electrons we're collecting. So it's new functionality that's available with direct detection technology that really isn't available with phosphor-based technology. And so that opens up, just new ideas, new ranges of research of using this electron counting, the amount of details in the pattern, energy filtering, for new applications of collecting data, new applications using pattern comparison, and can be used on all sorts of ranges of materials. So these are just some direct detection patterns from some minerals of olivine, kyanite, and quartz that can be really high-quality patterns. And in the case of these minerals, we can run at beam doses that are low enough that we don't have to worry as much about charging effects. We can run on a non-coated sample or without a low vacuum capability and still can get some results without charging effects influencing the patterns. Now, the third thing I wanted to talk about is analyzing deformed materials, because I think with direct detection we get some interesting information. So as we think about the detection geometry as shown there on the right, the electrons, as they enter the sample, they diffract and they scatter, and then they head back towards the detector. The electrons at the edge of the pattern have a longer path length through the sample than those at the center. So if we have a material that's completely undeformed, that means that signal is attenuated a little bit more. It has more of a chance to interact and lose some signal. But in deformed structures, it still has an opportunity to interact more with the crystal lattice. So if there's a higher dislocation density, then there can be a reduction of the sharpness of the diffraction towards the edge rather than the center, because it's sampling more of that defect density. And so we can see that in different patterns where towards the edge, the patterns become more diffuse. So this is an example from a niobium nickel silicon phase where the center of the patterns is very sharp, but the focus fades towards the edges. And in general, we've seen this, we've never quite been sure, how much of it is a lens effect versus how much of it is a sample effect. Well, now we know it's not a lens effect. It's a direct detection that we're applying here so that we can see the blurriness that's occurring as a function of electrons propagating through the material for different distances. And so, we've done some experiments where we adjust the tilt to adjust the path length through the material to be able to see that we can actually detect change in sharpness as a function of the path length through the material. So we can think of, perhaps measuring that blurriness and correlating a ratio of blurriness from the edge to the center to get some idea of the change. And so we can apply, so that's one idea for deformation. Of course, we can use it on deformed samples. So this is on a cold deformed iron powder. So we have a high level of deformation. We see that deformation there in the colors where the color's not solid. There's a lot of waviness to the color, a lot of changes. So the pattern changes a lot from point to point. But we can look at this, in this case, down to 200 picoamps. This was at 30 kV and 40 points a second. And even with a deformed structure, still get very nice resolution of the microstructure. That's sort of traditional EBSD for deformed structures. Looking kind of the clarity detector is compatible with what we call Prius. Prius is an approach where we use the EBSD detector as both an EBSD detector where we're finding the orientation interface from the pattern, but we also use it as a definable electron detector. So we can define different regions of interest on our detector and use those regions as basically electron counters. So as we raster the beam across the sample, we can monitor the signal flux on each of these. We can call them a virtual detector. And the position of these detectors will influence the type of contrast we have. And so traditionally, this has been done with having forward scatter detectors arranged around the perimeter of an EBSD detector. The advantage of using Prius is, one, we don't need additional physical detectors. We don't need multiple detectors. And two, we're able to virtually position these. So we can position them before the collection or even after the collection if we've saved patterns. And so here, the three defaults we generally use are towards the bottom, towards the middle, and towards the top. Of course, as we saw from the images, the signal level is highest in the middle. That's generally the one that's most sensitive to orientation contrast. Towards the bottom, we'll see orientation contrast and topography. Towards the top, generally, due to the tilt, it's more closer to seeing atomic number contrast. But we can generate all three of these simultaneously after a collection run to see these three different Prius maps. So clarity is present or is compatible with Prius. And once we have this data, we can look and see like our kernel average misorientation map. And the CAM map's a map that shows the local misorientation distributions. We can see that these form different cell structures within the microstructure, and they're very clearly resolved. It's basically blue and then a warmer color, but not a lot of speckling in those grains that we're able to resolve the misorientations pretty clearly. Going further, we can start applying the high angular resolution EBSD. So this is a piece of single crystal silicon where a micro indent has been applied, and then we've done an EBSD map around that indent. So if we look at traditional EBSD there in the middle, that shows the array of misorientations that have developed from the indentation. We can see how they're propagating around there. And the misorientation map there on the right shows the amount of misorientations that have been introduced through the indentation. Most of these misorientations are below 0.15 degrees. You can see those are the yellow boundaries there on the map on the right. So we have high sensitivity to misorientation using the clarity. And then we can apply this HR, or high angular resolution EBSD, where this is an approach developed by Angus Wilkinson. This is where we take one pattern that would be called the reference pattern. Traditionally, it's generally thought of being the known strain-free pattern. But of course, if you're looking at a deformed structure, it's selected as the best reference pattern. It may not be strain-free, but it's your baseline. And we compare it to another experimental pattern. So in this case, our reference is on the left. The pattern on the right is rotated 2 degrees, just to kind of give you an idea of a small change. For the silicon sample I'm showing, you can go away from the indent to get a single crystal pattern that's strain-free, and then as you're looking near the indent, you'll see the strain effects. So what happens with this approach is from the pattern, we define several regions of interest, or ROIs, that are defined between the two different patterns. Each ROI is compared using an FFT approach. These cross-correlations can find subpixel shifts. All these shifts, all the different ROIs are combined together to calculate this displacement gradient tensor to give an idea of the distortion and the rotational components of the change in the patterns between the two patterns. So this allows us to start thinking about measuring stresses and strains within the material. So these maps, this is produced showing a high resolution kernel average misorientation and then different stress components of the microstructure, showing positive and negative components of the result from the indentation. And so when we're using the clarity, this approach, because we don't have any of the phosphor effects, we have large pixels, we have direct detection. The information onto the sensor is much crisper, so we have a higher degree of sensitivity to pixel shifts than traditional phosphor-based detectors. And this is just an example. This goes back to the additively manufactured stainless steel sample, where we can see the orientation map there on the left. We run this through processing, and we can see through a geometrically necessary dislocation, or GND map there on the right, we see the dislocation cell structure that evolves during the processing of the material. And so we have a higher sensitivity to lower GND densities and can resolve the structure nicely. So just in detail, if you're not aware, one of the other things we released this year is our Apex data collection software. This is a new collection platform for both EDS and EBSD. And so Clarity is designed to run in the Apex platform. This is a little screenshot of that if you haven't seen it. And so my next slide, I think, is the summary. So again, this is the first direct detector commercially available designed for EBSD. It has high sensitivity, high pattern quality. It can be used for both pattern collection and mapping, and really has strong applications for beam-sensitive materials, for HREBSD, and I put here earlier adopters of technology. There's lots of new application space that can be developed with this. And so before I go to questions, I'm going to be a little bit brave, and I want to just kind of give a live demonstration of this. And so hopefully, through the magic of the internet, this will now share my screen. And so I'm just going to start. I'm going to bring up a collection. So this is a little shell program just showing the patterns that are being collected live. So you can see I'm just rastering over. In this case, I'm just looking at a piece of single crystal silicon. And I'm going to scoot it over, and I'm going to put it into spot mode so we can sort of see the pattern. So this is a single pattern here. And I'm going to press this little button so it shows us the statistics. And so what I want you to see, if you can see my cursor, this Z number is the number of electrons hitting a pixel. This here is the average and median values for all the pixels. So if I put my cursor towards the center, you can see I get about 1,400 electrons hitting that pixel. If I go out towards the edge, drops down to around 700, so again about a factor of 2. We come out towards the top, that drops down to around 300. So again, there's a strong contrast difference because of the intensity profile across that, but we can quantitatively measure the number of electrons hitting things as we interact with the pattern. And so, and this is non-background subtracted. This is just looking at the live image. But what I want to show is right now I have about 1 nanoamp of beam current. I'm going to drop this down to about 100 picoamps. You'll see that this gets darker because I had it in a manual range. So if I go full range now, we see the pattern. So visually, you can still see the diffraction pattern. If I look at my statistics, it's dropped down about an order of magnitude. So here now our average is about 70. And if we look in the center, about 100 electrons per pixel. And we can still visually see the diffraction pattern. And now I'm going to drop it down one more. I'm going to drop it down to about 10 picoamps. So here you can see that, there's less electrons. If I look at my statistics, we have about 10 electrons on average. We're about 14 there in the center. But visually, you can see the diffraction pattern still present even before the background subtraction. So it's very sensitive to low beam doses. We're not getting the noises that we typically get with traditional CMOS or CCD-based detection, because at low beam currents and low signal levels, those images become read noise dominated. And this detector has zero read noise. So we're able to still go to lower doses and still get a resolvable pattern. And so just to show, I'm going to close this shell and go to to apex here. And while that starts up, I'm going to go over, I have this set up just so we can see it on a polycrystalline sample. I'm going to be, this is where the limit of my brain multitasking will probably hit. I can only focus and talk so much at the same time. But I saved a position, so I think this will be somewhere on a polycrystalline sample. And this will be ready to, okay. All right, let's see. I may not have liked that I had my shell open at the same time before I did that. All right, well, we'll give that a second. So while that's loading, hopefully, I will see if there Well, let me check something while we're doing that. So while we're checking that, I'm going to look to see if there are any questions, just because we're getting close to the time limit here. So I'm going to pull up a couple here in our question and answer. So we have one question here. I understand the resolution is 500 nanometers. That's probably a little bit higher. Traditionally EBSD has a spatial resolution. If we talk about standard reflective EBSD, the best case number you're probably going to get is somewhere between 10 and 25 nanometers. That's going to be strongly dependent on whatever material you're looking at. And by that I mean if your atomic number goes up, it's a better reflector of the material. And so you get better spatial resolution because your material scatters more quickly. Your mean free path is lower. And so with regular EBSD and the clarity, we have the advantage of we can run at lower voltages, which will reduce our interaction volume to improve spatial resolution, but it will still apply to that. So I think we're probably still in that 10 to 25 nanometer range, but it's probably more easily accessible because we can go to lower voltages and be more efficient in terms of the collection. We've seen that with some different materials we've looked at, where if we look at it at 20 kV, we sort of see some grains, and as we go to say 10 kV, those grains are much more clearly resolved. Have another question here that just says, how low of a voltage can we go? The voltage threshold, generally the number we throw out is around 5 kV. The limit of the detection technology probably goes a little bit lower than that, maybe around 3.5, where our thresholding kicks in. The efficiency compared to phosphor screens is still much higher at lower voltages. It's not necessarily linear, but it's when we run at lower voltages, it's still pretty highly efficient for those low voltage type applications. And let's see here. One more question here was, what's the minimum number of electrons needed? Again, I think that's going to strongly depend on what material you're looking at and looking at the ratio of the diffracted signal versus the scattering signal. We've done experiments with, we use sort of like a nickel or stainless steel as a higher atomic number sample, and then we use something like silicon or aluminum as a lower number just to get us ranges of things. And in both of those cases, if we're trying to keep our indexing threshold high, that 10 to 15 electrons on average seems to be a good number for those materials. If you are, if you're willing to relax your indexing conditions a little bit and maybe use Enpar, factor of 2 or 3 lower seems to work pretty well. Okay, I think we'll go through. I got a couple more questions we'll go through. So one, it says, generally it said that megapixel resolution is useful for HREBSD. Do you plan to push the clarity to at least 1 megapixel? So what we found so far is that even though we have fewer pixels, our sensitivity to pixel shift is higher with direct detection. So rather than going to more pixels, we've just improved the sub-pixel sensitivity. And so at this point, we don't necessarily have a plan to go to higher yet, just because it would make the detector larger, and we start looking at what ports would be available for that sort of detector. But, we always have things on roadmaps of looking to say, how can we improve, detectors and hardware to improve, EBSD performance. So, but, we have seen that we're able to get high performance to the technique using just the number of pixels we have. I think it's more than just the number of pixels. And so with the detector, it's asking, do we get good patterns even when the sample is tilted below 70 degrees? Yes, we do. There is the caveat to that, though, is that as your tilt goes below, I want to say to maybe around 55 or so degrees, you'll start to see a contrasting version of the patterns. And so, and as you go below that, you generally have to increase your working distance so that electrons scatter towards the detector better. So if you go to lower voltages and low working distances, or longer working distances, you can still get EBSD patterns, but the contrast is inverted, and you have to invert that back for the HUF to work well, but it can still detect those patterns and analyze them. Okay, and we'll answer one final question, and then I'll go back to the slide deck. It says the discrete pole figure on slide 37, does each point represent each grain? I'm going to bring it up here so I answer it correctly. So on this particular point, each point doesn't necessarily represent a grain. It represents each pixel. Now, if the orientation within that grain doesn't vary very much, then those pixels will more or less overlap. But if there is some variance in the orientation within the grain, you'll see some scatter. It's not necessarily 1 pixel per grain in this particular representation. When using the software, it's certainly possible to just say, show me 1 point per grain, and then it will average the orientation per grain and show that on the pole figure. So with that, I'm going to go to some final slides. First, just would like to make you aware of some additional resources. So, we do a number of these webinars. These are available on our website. We have a blog where we more informally show information about products and applications at edaxblog.com. We have our different movies available on YouTube. We post things to LinkedIn and Twitter. And, of course, if you need more information about products or applications, you can reach us at info.edax at amatech.com. And then to make you aware, we have an upcoming webinar in a couple of weeks. Again, I mentioned Apex has been 2.0 is launched this year. So this is a webinar focusing on the features of Apex for EDS. What's new in key features, presented by Dr. Sheng Mu. And so if you're interested in this, you can register for that. And with that, I'd like to thank you for your attention. You're still able to submit questions. If there are more questions that come in, we'll address those offline. So thank you very much.